Hello, everybody. Good morning, good afternoon, good evening, depending on where you are. Thank you all for attending one more telecom seminar, which is hosted by Technology Innovation Institute in Abu Dhabi. I'm Dr. Daniel da Costa. I'm currently a principal researcher at Technology Innovation Institute. As many of you have followed up, we are running a series of telecom seminars along the last months, and they are being held on a bi-weekly basis. And today we have the telecom seminar number 12. So all the telecom seminars have been recorded and are available at the TII YouTube channel. Also, if you go to my personal homepage, you'll be able to see all the previous videos of the telecom seminars, as well as the upcoming telecom seminars. Okay, so for today, we are pleased to welcome Professor Bruno Clerckx from Imperial College London in UK. He will present and discuss the key principles of rate split in multiple access, some recent developments, emerging applications, and opportunities of rate split in multiple access for 6G networks. Well, Professor Bruno Clerckx has been a very active researcher in our scientific community, especially on rate split in multiple access, where he has published many seminal papers. He has also shared a new IEEE special interest group on rate splitting multiple access. And there is a website, and you can find many useful information about our SMA in that website. Specifically, there is a section called Best Readings. And in this section, you'll find many tutorials, magazine, transactions, letters discussing main aspects of rate splitting. For example, the basic principles, physical layer design, optimization, interplay between rate splitting, multiple access, and other emerging technologies, among others. Okay, so before moving on to the talk, let me introduce Professor Bruno Clerckx by reading his biography. So Professor Bruno Clerckx is a full professor. He is the head of the Wireless Communications and Signal Processing Lab, and the deputy head of the Communications and Signal Processing Group within the Electrical Electronic Engineer Department in Imperial College London, UK. He received the Master and PhD degrees in Electrical Engineering from the Université Catholique de Louvain in Belgium in 2000-2005, respectively. And prior to joining Imperial College London, in 2011, he was with Samsung Electronics in South Korea, where he actively contributed to 4G, 3GPP, LTE, LTE, IEEE 802.16m. He also had over 10 long or short-term visiting research appointments at various academic institutions around the world, and he is currently a visiting professor at Seoul National University in South Korea. He has authored 2 books on MIMO Wireless Communications and MIMO Wireless Networks. He has published around 250 international research papers and 150 standard contributions. And he is the inventor of 80 issued or pending patents, among which 15 have been adopted in the specification of 4G standard and are used by billions of devices worldwide. His research spans the general area of wireless communication and signal processing for wireless networks. He has been a TPC member, a symposium chair, and a TPC chair of many symposiums on communication theory, signal processing for communication and wireless communications in several leading international IEEE conferences. He was an elected member of IEEE Signal Processing Society Technical Committee. He served as an editor for IEEE Transaction Communications, IEEE Transaction on Wireless Communications, and IEEE Transaction on Signal Processing. He has also been lead guest editor for special issues of EURASIP Journal on Wireless Communication Networking, IEEE ACCESS, IEEE Journal on Select Areas in Communications, and IEEE Journal of Select Topics in Signal Process and Proceedings of IEEE. He was an editor for the 3GPP LTE Advanced Standard Technical Report. He received the prestigious Bronze Medal 2021 from France for exceptional work contributing to the progress of science in electrical and electronic industry. In the EURASIP Best Paper Award in 2022. He is a fellow of IEEE and he is a distinguished lecturer of IEEE Communication Society. So, Professor Bruno Clerckx, thank you once again for accepting our invitation. And without further ado, the floor is yours.
Thank you very much, Daniel, for the kind introductions and for the invitation. So today, indeed, I will be talking about rate splitting multiple access and for 6G. And I would like first to thank many collaborators around the world, starting with my PhD students and postdocs and people in various institutions. This is just a subset of institutions we have collaborated with on this topic. It has been a growing number of collaborators in the past 12 months that I cannot list here. So today, let me flip. Today I will be talking about this, what you see on the screen. So I will start first with reminding what multiple access techniques are and the different techniques that people have been looking at. I will jump into rate splitting multiple access, looking at the fundamentals. Then I will look at the interplay between RSMA and different other techniques, different systems and other techniques. Look at the physical layer design and then draw some conclusion. So let's start with multiple access techniques. So we're all familiar with this concept, and we all know that wireless communication systems are inherently multi-user systems. And the question is, how do we serve those multiple users? And you have two basic building blocks in communication. You have the downlink setting and the uplink settings. The downlink is usually modeled as a broadcast channels information theory, and the uplink as a multiple access channels. And so in these talks, we'll talk about both, but I will primarily focus on the downlink. Right, so in the downlink, you can have, for instance, a scenario where you have M antennas at the transmitter, and you have K users, in this case, for instance, K single antenna users, but you could have multiple antenna users as well. And you have here trailer state information of user 1 to user K between the transmitter and the receiver. And then similarly, on the uplink, you could have M antenna at the receiver, you can have K users that are transmitting on the uplink across those K vector channels, H1 to HK. And in communication, the first metric that comes to mind when we want to design the systems is rates, and we want to maximize the rate. So we can have per user rate, some rates, minimum rate that we want to maximize, and so on. And one notion that will come back throughout this talk is the notion of degrees of freedom or multiplexing gain that simply reflects the slope of the rate as a function of the SNR. So if you look at the rate of a given user, okay, and you look at the high SNR behavior of this rate, you can see that actually this rate can be written as a pre-log factor multiplied by the SNR in dB. And this pre-log factor is what is called DOF, or multiplexing gain. So it's the slope of the rate versus SNR. And so you can have here, DS would be the sum DOF or sum multiplexing gain, because I'm looking at the sum rate here. So it's the pre-log factor of the sum rate, or is the slope of the sum rate versus SNR. And so here, if you have why it's important, is simply because in this example here, on the right side, if you have two users and two transmit antennas, and you have two different schemes, one in red and one in blue, which one is better? Well, the larger the DOF, the faster the rate increases with the SNR. So you would prefer having a scheme that has a higher DOF. That's the reason why it's preferable. Essentially, the system will make use of the SNR more efficiently if you have a higher DOF. Right, so what does information theory tell us about this scenario where we have a transmitter that want to serve multiple users? Well, if you have single antenna nodes, so you have single antenna, the transmitter, and all those receivers, we know that the capacity achieving strategy is called superposition coding with successive interference cancellation, which is nowadays known as power domain NOMA, non-orthogonal multiple access. So this is one strategy. The other strategy that you could use is dirty paper coding. Now, if we move to multi-antenna settings, we know that doing superposition coding with SIC or doing power domain NOMA would lead to a performance loss, and the only capacity achieving strategy or known capacity achieving strategy is dirty paper coding. And this is true as long as the channel is perfectly known at the transmitter. If the channel is imperfectly known at the transmitter, as you would have in typical systems, the capacity is still unknown, and so the capacity achieving strategy is also unknown. Right, but in practice, well, we don't really look at, or we don't use dirty paper coding. We use various multiple access. And so one of them is OMA, orthogonal multiple access, and you're all familiar with this in the form of PDMA, DMA, CDMA, or WAVE-DMA. Essentially, you eliminate any multi-user interference by locating orthogonal radio resources. And this has been used extensively in those previous generation of communication systems. Another strategy is SDMA, space division multiple access, where we use a spatial domain to multiplex users using multi-user linear precoding. And this has been extremely popular in the past 20 years and is used in 4G and 5G extensively in multi-user MIMO, in network MIMO, millimeter wave, massive MIMO, and so on. And there what you do is that you have K messages, you encode those K messages into K stream, you linear precode them, and so those precoder creates essentially K beams. And at the receiver, and each of those receiver, any multi-user interference that is remaining is treated as noise by those receivers. So the important bit here, when you do SDMA, is that the interference is treated as noise at the receiver. Right, then you can do NOMA, so superposition coding with successive interference cancellations, or simply SIC. So here you have two code words for user 1 and user 2. You superimpose them in the power domain. And then you have one of those two users, the strong user, will decode the code words of the other user. So in this case, user 1 will decode the message of user 2 using SIC, and then will decode its own message, while user 2, the weaker user, will treat the interference from user 1 as noise. So what's the big difference with the previous strategy here, where we treated interference as noise? Well, in NOMA, it's the opposite. One user, the strong user, will fully decode the interference because he will fully decode the message of another user. So that's a completely different interference management strategy that is based on decoding interference. You can do NOMA in a multi-antenna settings, and a lot of people have been doing that, but you have to be very, very careful at what you're doing. And this is one of the reasons why we wrote this paper, because of lots of misunderstanding and misconception has been propagated in some of those multi-antenna NOMA papers. And the issue with this, when you do multi-antenna and NOMA, is that you force one of the users, each of those groups, for instance, this user here is forced to decode the message of the other users. And the problem with doing that is that it leads to a loss of the multiplexing gain, or loss of the DOF. And this loss comes at the expense of a high receiver complexity because you have to use SIC. And so this is a really major problem when you do multi-antenna NOMA, and we have to be very careful about this. So I will not spend time on this issue here. This is the topic of another talk, but you will see the consequence of this drawback of multi-antenna NOMA throughout the presentation. Right, so now let's look at rate-splitting multiple access. So what it is. So the first thing we have to notice is that this whole notion of orthogonal versus non-orthogonal, in my opinion, this is really not a problem. It's not the problem, it's not the central problem when we design multiple access. After all, when you look at SDMA or multi-user MIMO in 4G and 5G, this is already non-orthogonal. We have multiple users share the same time frequency resources, and they interfere with each other. The real problem when you design multiple access is how you manage interference. And so in OMA, there is no interference to manage because you have completely avoided it. In SDMA, you treat interference as noise, and in NOMA, you fully decode interference. And what we know from information theory, from this very well-known paper from 2008, is that if the interference is weak, you should treat it as noise. If the interference is strong, you should fully decode it. And if the interference is in between, what you should do, you should partially treat it as noise and partially decode it. What you shouldn't do is treat interference as noise when the interference is strong, or you shouldn't try to fully decode interference when the interference is weak. And so if we think about this, we take this lesson and we think about this in terms of multiple access, what do we have? In SDMA, we treat interference as noise. And so that means that this will really work well whenever the residual interference is relatively weak, but it will not work well when it's medium or strong. NOMA is the opposite. NOMA fully decode interference, so it would operate better when the interference is strong. That's what we have here. But it would not work well when the interference is weak or when the interference is medium level. And rate-splitting multiple access enables to essentially bridge those two extremes of weak interference and strong interference levels, that it can flexibly manage interference, whatever the interference level that we have. So, rate-splitting multiple access is a multiple access scheme that relies on the rate-splitting concept, and I will see in a moment what it is, that was invented by Caroline and Han and Kobayashi in late 70s and early 80s, originally introduced for the SISO, single antenna interference channels, and it has grown in the past few years, not for the interference channels, but especially for the broadcast channels, when you have multiple antennas and you're doing downlink scenario. But you can use it in the uplink as well. And the particularity of this multiple access is that it's general, it's flexible, and it's robust. It's general because you will see that existing schemes like SDMA and NOMA and multicasting are actually particular instances of this RSMA framework. It's flexible because it's enabled to actually cope with any interference level that we have in the system, whether it's weak, medium, or strong. And it's robust because it's actually information theoretically proved to be DOF or multiplexing gain optimal when we have imperfect knowledge of the channels at the transmitter. And the key of our splitting multiple access is to be able to partially treat interference as noise and partially decode it. And this enables to really bridge the two extremes of SDMA and NOMA by adjusting how much is treated as noise and how much is decoded. It was explained in lots of detail in this paper that now received the best paper award in this year. So let's look at this two-user architecture. And if you understand this, you understand the key architecture of RSMA. So let's start with two users. I have W1 and W2. I have two users, sorry, here on the right side, a user one here with a receiver of user one. And I have user two with a similar architecture as user one. And I have two messages that I want to deliver to user one and user two. So blue for user one and red for user two. And what I do is that I take those two messages, and instead of encoding them directly into two streams, as I would have done, for instance, in SDMA here, where you take those K messages and you encode it to K streams, in RSMA, I don't do that. What I do is that I take those two messages and I split them into two parts. A blue part here and a blue part there. This is called a common part, and this is a private part. And I do the same for the red message as well. And then from those two parts, I combine them into this new message WC. It's called a common message. And now I have three messages, effectively. From two messages here, I have created three messages. And these two messages here, I will encode into SC. I will encode into what is called a common stream. While those two messages here, I encode them into two private streams. So what's the difference between a common stream and a private stream? Well, a private stream is simply decoded by its intended receiver, its intended user, and is treated as noise by other users. While the common stream is a stream that is decoded by multiple users. And so SC, S1 and S2 are now pre-coded, and what we end up with is a sum of three pre-coded streams, as you can see here on this system model. And so importantly, again, we go from 2 messages to 3 streams. And what do we do at the receiver? Both receiver, user 1 and user 2, they decode SC first, they decode the common streams, they retrieve from the common streams WC, and user 1 from WC will retrieve the part of WC that is intended to itself. They will retrieve the blue part that is intended to user 1, then will perform SIC, and then will retrieve S1 that carries WP1. And so you see that user 1 recovered WC1 and WP1 that were the 2 parts that were split at the transmitter. And then we'll recombine those 2 into the original message. And user 2 does the same thing by decoding the common stream first and then decoding its private streams. And so by doing this, what's happening is that essentially both users will partially decode interference because both of them will partially decode part of the message of another user through this presence of these common streams. And so it's called rate splitting because the rate of a given user has been split into multiple parts. And in this case, it's been split into 2 parts. The rate of user 1 will come from the rate of its private stream S1 and part of the rate of the common stream that carries WC1. Right. So where is SDMA and NOMA in this scheme? Well, if you turn off the common stream and you force W1 to be encoded into S1 and W2 to be encoded into S2, you end up with this system model here. And this is just a particular instance of rate splitting multiple access when you actually allocate 0 power to the common stream. The NOMA schemes I was talking about before is the same concept, but different way of actually obtaining it. Is here you turn off the private stream S2, so you use only 1 private stream that is used to encode W1. W1 goes directly into S1, and W2, instead of it being encoded into S2 as we have in SDMA or in MULP, W2 in NOMA is encoded into the common stream SC. So W2 goes into the common stream SC. And now what we have is a common stream SC that carries W2 that is encoded and a private stream S1 that carries W1. Why this is NOMA? Because again, what we have here is that both user will decode SC, both user will decode W2. And this is exactly what we have in NOMA. In NOMA, the strong user decode the message of the weaker user so that both users decode the message of the weaker user. This is exactly the multi-antenna NOMA scheme. So you see those 2 schemes is a particular instance of rate splitting multiple access. Another way of looking at this is the following. We have 2 messages to transmit and we have 3 streams. 2 streams that are private, so that means that any interference that we have between those 2 streams would be treated as noise. And 1 stream that is common, that means actually both users will decode that stream. And how does all those multiple access schemes differ from each other is how we map those 2 messages to those 3 streams. In SDMA, we take the 2 messages and we map them into the private streams. In NOMA, we take one of the messages, we map into one of the private streams and the other one into the common streams. In OMA, you just use one of those 2 private streams, you transmit to one of those 2 users. In multicasting, you take those 2 messages and you encode them jointly into the common stream so that both users decode those 2 messages. And in rate splitting, you split messages such that essentially part of it goes into the private streams and part of it goes into common. Part of it here goes into private and part of it goes into common. So you see from this table, rate splitting or rate splitting multiple access here is a very general framework that encompasses SDMA, OMA, NOMA, and multicast as particular instances. Right, so how do we split messages? This is an example here. For instance, imagine you have 4 bits for user 1 and you have 3 bits for user 2. And if you do MULP, for instance, you will take those 4 bits and imagine that you encode this into a 16 QAM symbol. In user 2, you would 3 bits, you map this into 8 PSK symbols. While with rate splitting, we take those 4 bits and we're going to split them. We can take, for instance, 2 bits for the common part, 2 bits for the private part, And here for user 2, 1 bit for the common parts, 1 bit, 2 bits for the private parts. And then here I will create WC by taking those 2 bits from user 1, this 1 bit from user 2, and I will create a new message with 3 bits, and I will encode this into, now let's say, map this onto an 8PSK symbol. So I will have 8PSK symbol for the common streams. I will have a PSK symbol, for instance, for private streams here for user 1, and a QPSK for private stream of user 2. And at the receiver, both receiver will actually decode the common streams, and user 1 will retrieve those 2 bits, and user 2 will retrieve this last bit here, and will recombine with its private parts. Right, so this can be obviously optimized depending on channel conditions and so on. But what happens if we have k users? That was 2 users, where we show nicely that rate splitting encompasses all those existing schemes. If you have k users, you have this 1-layer rate splitting architecture here, 1-layer RS, which is a particular instance of this RSMA framework. And this is probably the most popular architecture because it's the simplest. Essentially, it says that if you have k messages, you split k messages into common parts and private parts, and you create 1 common stream and k private streams. And so at each of those receivers, you have 1 SIC. Each receiver decode the common streams and then will decode its private stream. So user K decode SC, retrieve the part that is intended to user K, perform SIC, and then decode its private stream SK, and then recombine into the original message. So here, MULP and SDMA is actually still a subset of 1-layer RS. If I turn off common streams, I end up with the classical multi-user linear precoding that we have in 4G, in 5G, in massive MIMO, and so on. The NOMA schemes is not a subset of 1-layer rate splitting. As long as k is larger than 2, if k is equal to 2, then NOMA is a subset. But for k larger than 2, NOMA is not a subset of the scheme. So this is actually a different type of schemes that is very interesting because it has only 1 SIC. And you will see that this 1 SIC can give you significant performance enhancement over MULP and NOMA. Right. So what if you have now, let's say, multiple antennas at the receiver? So not only 1, but multiple. So what you can do is that you can extend this 1-layer rate thing, where we have, instead of having vectors, you have matrices, precoding matrices. And instead of having a stream, a common streams and a private stream for those users, now you have a vector of common streams and a vector of private streams because of the multi-antennas that you have at the receiver. So this can be done as well. Right, what if, can we have multiple splits and can we have multiple SIC? Yes, we can do that. So for instance, here, this is the general form of rate splitting multiple access, much more complicated because you take 3 messages and you split into multiple parts. Some parts is encoded into private streams. Some parts encoded in streams only decoded by 2 users, as you see from the indices of those S here. And then some parts decoded by all 3 users. And here we can show that in this framework, multi-user linear precoding, or SDMA, and NOMA are always subset of this architecture. And so the usefulness of this is that if you can run this and optimize this, you can identify very quickly what are the messages that give you the most performance gain in a specific propagation condition, and you can tailor this architecture to the propagation condition or the application that you're interested in. The 1-layer rate splitting architecture, the previous one that we had here, right? Where is this one in this general architecture? Is by only keeping this stream here, 1 common stream, and 3 private streams. So we turn off the one in the middle here. That would be the 1-layer rate splitting. Simpler, only 1 SIC. Right. So far I talked about linear rate splitting or linear precoding when we have in rate splitting. You could have also non-linear precoding. And so, for instance, here you could have a private part that you encode using non-linear precoding. For instance, here, dirty paper coding. And why this is interesting? Because now you end up with a superposition between the rate splitting and the dirty paper coding. We know that dirty paper coding is capacity achieving when we have perfect CSIT, but we don't know what is capacity achieving when we have imperfect CSIT. And so if you optimize this architecture, you will see that as your CSIT quality becomes close to perfect. Essentially, this architecture boils down to DPC. Only this part of the scheme is useful. But as the CSI quality of the transmitter degrades, you have more and more power that is allocated to the common stream and less power to the private streams. You could use, instead of DPC, you could use conventional narrow map recording or vector perturbation, and so on. So that's to show you how RSMA is a superset of various strategies, SDMA, multicasting, NOMA, and the most popular RSMA strategy is one-layer rate splitting because it has only one SIC, but you could have architecture with two SICs, and you could have the very general framework of RSMA that encompass all those techniques. Right, so on the uplink, you can also do RSMA, and so the way it works is that now you have two messages, W1 for user 1, W2 for user 2, and what you do is that again you split W1 into two parts, a first part and a second part. And what you do at the receiver will decode the first part of user 1, and will decode the second part, will decode the message of user 2, and then will decode the second part of user 1. And what that enables you to do is it enables you to achieve the capacity region of an uplink system, so a multiple access channel, by avoiding any form of time sharing. So if you don't split the messages, what you have to do is that you can achieve those corner points, but achieving any point in between would be done by doing time sharing. With RSMA, you don't need the time sharing because you can allocate different power to those different messages, different streams here, and you can achieve any point on this boundary without doing time sharing. So this is very helpful in emerging systems where you have low latency constraint and things like that. So this is actually not new schemes on the uplink. On the uplink is what's actually invented by in this paper in Rimoldi Nobranche in 96. You can see from this, the uplink and downlink RSMA actually two different strategies, but they both rely on the key principle is to split the messages. And in both cases, the OMA, NOMA is both of them are always a subset of RSMA. NOMA here is obtained by essentially allocating zero power to one of those two streams. So we don't split the messages and you end up with the classical NOMA strategy. Right, so let me show you what's the benefit of all this. So first benefit is DOF enhancement. So you increase the slope of the rate versus SNR. So here you have two examples. You have here a certain quality of the CSI, the transmitter. You have in blue SDMA, multi-user MIMO. In red, you have RSMA. And what you see here, when you have two antennas, you have a slope of 1 in this case, and you have a slope of 1.5. So you have 50% increase in the slope that is achieved by rate splitting over SDMA. In terms of region, so your degrees of freedom region, instead of looking at rate region, you're looking at this in terms of degrees of freedom. This is the region that you achieve with rate splitting. This is what you achieve with SDMA, and the dashed line is, or the dotted line is with NOMA. And what we see here is this region and this slope here is the best performance you can achieve. So you cannot have degrees of freedom higher than that. This is proven by information theory. And so we know now that we don't know what is capacity achieving when we have imperfect CSIT, but we know that rate splitting, the framework that I showed you, is at least optimal in terms of DOF. So it's very much grounded into some fundamental information theoretic principles. Right, so let's look at DOF versus number of SIC, right? So number of SIC would be a measure of the complexity of your scheme, and your DOF or multiplexing gain would be a measure of how good, the spectral efficiency is. And I have two metrics here. On the left, I have some multiplexing gain, some DOF, and on the right, I have MMF multiplexing gain. So MMF stands for max mean fair. And what that means is that I'm looking at the pre-log factor of the sum rate, that's what I have on the left side, and I'm looking at the pre-log factor of the minimum rate among K users, that's on the right side. So this is really more for maximizing throughput. This is really more for maximizing kind of fairness among users. What you don't want to do is to have a scheme that has many SIC and low multiplexing gain. So being in this region is not good. This is low performance, high complexity. And this is what you see here with some NOMA schemes. So this is really a scheme. Typically, when you have one group, you have all key users into one group, and one of those users decode the message of all the other users. Very low multiplexing gain and very high complexity. So that's the issue I was mentioning at the beginning. When you do multi-antenna NOMA, be very careful because you can have very low multiplexing gain and high complexity. If you have MULP SDMA, it's much better. You have no SIC. It works okay when you have some multiplexing gain, but it doesn't work so well when you have minimum fair multiplexing gain, especially in scenario where you have more users than the number of antennas. If you have only one SIC, you see where rate splitting brings you. It outperforms for both multiplexing gains, both sum and MMF multiplexing gain. It outperforms all those existing multiple access schemes, and it does this with only one SIC. This is achieved by only having one layer rate splitting. Right. So what is, you can also look at the number of users that can be supported by rate splitting and by other multiple access schemes. So this is how we can measure this. We're looking at what is the multiplexing gain versus the number of users that we have in the systems. And so the multiplexing gain will decrease as the number of users essentially increases. And if you want to achieve, for instance, a multiplexing gain of 0.1, so you want that your minimum rate scales at 0.1 multiplied by log2 SNR, what you see is that if you have MULP, like in purple here, well, you will not be able to satisfy this constraint of 0.1 once you have 7 users. So the MULP or SDMA here with 6 transmit antenna would be able to support 6 users, but will not be able to support 7 users. That's what it says. If you do NOMA here, you can support with achieve 0.1 DOF, you can support 10 users. That's better than MULP, but this comes at a cost. And the cost is that you need 9 SIC. So you need to implement 9 SIC at each user. This is impossible. And rate splitting here, one layer rate splitting, and supports 15 users to achieve a DOF of 0.1, and does this with only one SIC. And again, the reason why you have those DOF gain is because you do not force yourself to fully decode interference like in NOMA. You do not force yourself to treat interference as noise like in SDMA. You have the ability to partially decode and partially treat interference as noise, and that brings you this enhancement even if you have only one SIC at the receiver. So now you can optimize the systems, and what you have to optimize here is the precoders for the common and the private. You can write the rate of user K. You can write the rate of its private common part, the private part, and then you can formulate the whole optimization problem using your favorite convex optimization method. Try to maximize and find the precoding matrix, so the precoder of the common part and the private part, and find C, which is the vector of the common rate. That's what C is a vector of rate CK, and CK is the portion of the rate of the common stream that is intended to user K. So this is an important part, is essentially the portion of the common stream rate carries that is intended to user 1, that is intended to user 2, user K, and so on. And each of those parts needs to be optimized depending on the objective function that you have. So let me show you some results before we look at some applications. So this is a perfect CSIP setting here where I have multi-pair coding in blue. That's the capacity region, so you can't beat this. In yellow, we have NOMA. In green, we have multi-user MIMO, MULP, SDMA. And in red one, we have rate splitting. So you see how the rate splitting really outperformed those 2 existing schemes. Because is actually those 2 schemes actually particular instance of rate splitting in these 2 user setup. What if you have 2 transmit antennas, but now you have 10 users. And so you really want to serve those 10 users. And this has been really a heavily overloaded system that has been really advertised by the NOMA literature and claimed that NOMA would be a good strategy in this. And what you can see is that if you have SDMA with 0 SIC, you achieve this performance. If you do NOMA, yes, you achieve better performance in this overloaded setting, but you need 9 SIC to achieve performance enhancement. If you do rate splitting or rate splitting multiple access, you have only 1 SIC and you significant performance enhancement over NOMA and SDMA. Right, so what if we have imperfect CSIT? So in the perfect CSIT here, DBC was better than rate splitting. In the imperfect CSIT, now we have DBC in blue, we have still SDMA and NOMA here, but now we have rate splitting and dirty paper coded rate splitting in red and purple that outperform DBC. And so we don't know what is capacity achieving when we have imperfect CSIT, but what this shows you is that you can have simple 1-layer rate splitting architecture, 1 SIC, linear precoding, and that would outperform non-linear precoding techniques like DPC that is capacity achieving when we have perfect CSIT. So that shows you how robust rate splitting is to imperfect CSIT. Other results here with imperfect CSIT, again, what you see is that you have all those classical baseline, different NOMA schemes and multi-user linear precoding or SDMA here as well with different SIC for NOMA, and the rate splitting always significantly outperform those different schemes with just 1 SIC. Another scenarios, this is a different metrics. This is a robust max-min fairness. So you try to maximize the minimum rate, but on top of this, it's robust in the sense that you have your CSI is imperfect and is bounded within the ball. And so what you try to maximize is the minimum rate for any channels that can occur within that ball. Now what you see is that you get performance enhancement over SDMA across a wide range of SNR. Right, so what is the main observation that we have with RSMA is that it partially decodes interference and partially interference as noise. That's really key, and that's you can do that because you split your messages, because you use rate splitting techniques in your multiple access. It enables you to bridge the stream of SDMA and NOMA, so it's more powerful and more general than any of those baselines, and that leads you to having schemes that one multiple access schemes that does all those different schemes at once. So there's no need to talk about OMA, SDMA, NOMA, and all those variants. You have only one schemes, and that perform everything. The rate of RSMA is always superior to SDMA and NOMA because SDMA and NOMA are always particular instance of RSMA. And what is important is that it's optimal from a DOF perspective in both perfect and imperfect CSIT. So perfect CSIT, this is not surprising, but imperfect CSIT, this is very recent. It's more driven by the information theoretical literature in the past few years. The achievability has been shown in those 2 papers, and the converse has been shown in those 2 papers here by Sayed Jafar's group at Irvine. And so what you can show is that if you take rate splitting schemes, the DOF that you achieve with rate splitting matches the outer bound that you achieve using those converse methods that have been derived in those papers. You can't get anything better than that in terms of DOF. It copes with any user deployment. It means actually whether you have a diversity of channel strength, whether you have different directions of user, whether you have different CSIT accuracy, whether you have different network load, high network load, overloaded or underloaded. And so all those benefits come with a lower computational complexity than other schemes that rely on SIC as well, like NOMA, because again, you do not force yourself to decode the message of another user. This is sometimes a very bad idea because you're not in a regime where you should fully decode the message of another user. You have to have the flexibility to adjust depending on your conditions. The drawback is that you have a higher encoding complexity because with 1-layer rate splitting, you go from K streams to K+1 frames. So there you have a higher encoding complexity. Right. Let me skip this and let me look at some interplay with other techniques. So, because it's quite fundamental communication theoretic ideas, whenever you have multi-user interference or multi-user systems, this notion of rate splitting and rate splitting multiple access can come into play and give you some benefits. The gain would really depend on the specific application, the number of antennas, the propagation condition, the number of users, the metrics you use, the CSIT quality, and so on. So here you see a subset of all possible applications where people have been looking at, and I will, in all those applications, people have shown that RSMA outperforms SDMA, NORMA, and NORA. What I will do, I will quickly talk about the one highlighted in blue very, very briefly. Right. FDD massive MIMO, challenging because you don't know the CSI accurately at the transmitter because of lack of reciprocity. Typically, what you do is that you do a two-tier precoding. So this is known as two-tier precoding or JSDM. For instance, you have multiple users that are relatively close to each other. They share similar second-order statistics. And what you do a first precoder that tries to separate those different users into different groups, so avoid intergroup interference. And then you have a second precoder that tries to eliminate interference between users. The issue with this, the drawback, is that you could have two forms of interference. If you don't know perfectly your covariance matrices, or if the covariance matrices of those different groups overlap with each other, you will have intergroup interference. If your CSI is not accurate enough, you will have interference between those users. And so you can design rate splitting techniques specifically for this setup. And you can show it here in brown that actually this, what is called hierarchical rate splitting, relies on 2SIC, outperforms all the existing baselines for various CSIT conditions and overlapping between covariance subspaces. TDD massive MIMO. So in TDD massive MIMO, it's easier to obtain channel estimate at the transmitter, at the base station, but you may still be subject to the imperfections. And one of them that is very important is mobility and latency. So between the time where you estimate your channel on the uplink and you use a channel estimate to actually do precoding and data transmission, there might be a lag, a few milliseconds because of the processing delay. And this, a few milliseconds can lead to a change into the wireless channel. So this is called CSI aging, essentially. And what that means is that your throughput with SDMA can drop quite significantly as your user speed increase, just when you have 10 milliseconds delay between your CSI acquisition and your transmission. With rate splitting, what you have is actually you have a much smoother degradation, and so you can maintain multi-user connectivity at much higher mobility conditions. This is actually real throughput based on real link level simulations I will briefly talk about later on. Cooperative rate splitting. So this is another strategy where you enable cooperation or relaying among receivers, among users. Those different users, they will decode the common streams, and so they can now share that common streams with each other in order to increase the performance, the decoding of the common stream, the rate of the common streams, and therefore their respective rates. And this outperforms all existing strategies again, even and provides significant gain even at low SNR. Cloud radio or CRAN, Cloud Radio Access Network. So here the issue is that you have multiple remote radio heads, you have front haul links, and those front haul links, they have limited capacity. And so what you need to do is that you need to manage the interference that actually those different RRH create to each other when they want to serve multiple users, but you have to account for the limited front haul capacity. And so those are two different strategies. On the first one, you do a one-layer rate splitting, and then you do compression before you transmit over the front haul. The other one is that you do a rate splitting, you split the messages, and then you decide which of those sub-messages or those sub-streams, common stream, private streams, and so on, is transmitted to which RRH, those different strategies. And those papers have shown that whatever technique you choose, the RSMA always outperforms SDMA and NOMA from a spectral and energy efficiency perspective. Intelligent surfaces, this is also a popular topic, where you can use intelligent surfaces as part of the wireless environment in order to try to dynamically change or engineer the wireless channel. And that gives you lots of performance enhancement, especially when you don't have a direct line of sight between the transmitter and the receiver. And here you can really combine the benefit of IRS or RIS with RSMA. And this is what we show here. In blue one, in green one, you have NOMA, in red one, you have SDMA, and in black one, you have RSMA. It gives you, this combination interplay gives you higher spectral efficiency, you have a better beam control flexibility, and you increase the coverage. It's robust CSI imperfection and user mobility. And this is a particular issue with those intelligent surface where CSI acquisition is actually more difficult. So it's the robustness of RSMA really helps in that setting. And you can lead also, the RSMA enables you to use less complex RIS hardwares because of the superiority of RSMA over other multiple access schemes. Non-orthogonal multicast and unicast transmission. So this is a completely different setting. Is what if we want to transmit multiple unicast messages? So that means a message that is intended to only one user, but I have multiple of them, so as we do in multi-user MIMO. But on top of this, I want to transmit a multicast message that is generally intended to multiple users. And for instance, here I have 3 users. Each user will want to receive its intended unicast message in green, yellow, or blue. And on top of this, there is a red message that is really intended to all those 3 users. For instance, you want to watch BBC News, and all those 3 users want to watch BBC at the same time. So that would be our multicast message. And so one way of doing this, you can separate multicast from unicast using orthogonal multiple access. For instance, you do MULP on one side for unicast, you do multicast on another resource. There is no interference. This is not very efficient. What you could do is that you could superimpose them into non-orthogonal unicast multicast. And so what you would do, for instance, here, I have a multicast message here, W0, and I have unicast message W1 to WK. And I superimpose them in the power domain, and I use one SIC, where this SIC is used to decode the multicast message and then decode the unicast message for given users. So this is one architecture you could do. This is not done in 5G. Maybe it will be done one day. But you could do better than that if you do rate splitting. What you could do, you could take those K messages, you split them here, you split them into common and private parts, and now you encode part of those unicast message together with the multicast message. And at the receiver, you do one SIC, and you retrieve the multicast message, you retrieve the part of your unicast message and the other parts. And that architecture here enables you to use the SIC more efficiently to separate the multicast from the unicast, to separate the pink one from the other unicast message, but also better manage the interference between unicast methods. And that gives you also performance enhancement over doing this kind of method or doing OMA kind of transmission. Right. Another scenarios, multi-beam satellite systems, completely different application. And multi-beam satellites, they're often modeled as multi-group multicasts. That's what we see here. So imagine this is one beam. You have a geostationary satellite. You have many different beams on Earth. And in each beam, you have multiple users to serve. And all the packets of those different users, typically, they actually encoded jointly and multicast it within that beam in order to increase the coding gain of that, that transmission in that beam. So that's why you end up with a multicast transmission in a beam, and each beam forms a different group. You have multi-group multicast. And this is a typically overloaded scenario where you have quite a bit of interference between those different users. You can have imperfect CSIT as well because of the latency between the geostationary satellite and Earth. And you have on top of this, you have very tight power constraints at the satellite feeds. And what you can show is that here in this example, where you have 7 beams and 14 users with 2 users per beams, you see the minimum rate that you can achieve versus the power used at the antenna, at the satellite. In red, you have rate splitting. In blue, you have MULP or SDMA. And you see how much watts you can save at the satellite. If I have perfect CSIT, the solid line, you would save here, I don't know, 70 watt or something at the satellite, which can be very, very significant for satellite application where they really do not waste any energy. What if you have short block length? So this is really important when you have low latency application. And what this figure shows you is that the solid lines is what you get with RSMA and SDMA when you have finite block lengths. And you see as your block lengths increase, essentially, the sum rate of those 2 systems increase. The dashed line is what you get in the limit where your block length becomes infinite long block length, and then you end up with essentially an expression log to 1 plus SI now. What you see is that this crossover point here, that what it tells you is that RSMA in blue would achieve the same sum rate as SDMA, but it would do that at much smaller block length. You could do this with a few hundreds in terms of block length versus infinite block length for SDMA. So that tells you that you could use RSMA, get the same performance as SDMA, but achieve a much lower latency because you can use shorter block lengths. Another scenario, integrated sensing and communication. So here the question is how you make the best use of the spectrum to sense, to do radar sensing, and at the same time do communication. So you have already the challenge of managing the interference between all those different users when you have communication. But on top of this, you want to use the architecture and the hardware and the processing to also sense in some other directions. And so there is a trade-off now between the rate you achieve for those communication users and the sensing performance that you achieve for your target. For instance, the direction of arrival or departure estimation, your radar cross-sections, your Doppler estimations, and so on. And so what we can show is that there is indeed a trade-off between the communication performance, here this is the minimum rate achieved by those different users, versus the performance of the radar that is measured here in terms of primary arrival bound. And there is a trade-off, and the rate splitting outperforms clearly SDMA and NORMA in all those different radar communication, integrated communication scenario. Again, because you have the flexibility of managing the interference in a very smartly, and on top of this, you have the presence of the common streams that you can also use to actually better sense in the directions of interest. Right. Before I conclude, let me look at physical layer design. So what I've talked about so far is physical layer, but assuming primarily we have infinite block lengths and Gaussian signaling. I mentioned briefly about finite block lengths, but overall it was always Gaussian signaling. Now, in practice, you don't use that. You use finite constellations. You need to design those constellations. And so what you end up with in this, for instance, here, 2 users, 1 layer rate splitting is you have those 2 messages, and then you have your message split. You have the encoder, we use polar codes. You have interleaver, you have adaptive modulation, all the way to 256 quants, like in 5G. And then you have to design your receiver. And in this case, you may have imperfect SIC, imperfect cancellation, because your channel code is not infinitely long. For instance, your block code is not infinitely long, so you may have imperfect SIC. You may have to do link adaptation because you have to adjust your modulation encoding rate dynamically as a function of the channels for all those 3 streams, common and the 2 private, and so on. And what we can show is that this line is Shannon bound when we assume Gaussian signaling, as we have done before, and the solid lines is the real throughput, link level simulation, the gap that we have between those two comes from the finite block length of the polar code. But you see that the RSMA always outperform SDMA and NOMA in these two user settings here. And again, at link level, simulation is actually appears larger than actually Shannon bounds level. Same in multi-group multicast. So this is a scenario here where you have a solid line is Shannon bounds, dashed line is link level, and you see the significant gain that you get at link level. If you want to achieve, I don't know, 1.5 bits per second per hertz, you gained I don't know 15 dB SNR versus doing multi-user linear precoding at the real link level. This is massive MIMO application kind of. So here we have from low MIMO, 4 users, 4 antennas to 8 users, 32 antennas, different mobility. Red one is what you have in 5G. Essentially, you want to serve, let's say, 8 users here, but at some point you saturate. It becomes very difficult to cope with the multi-user interference because you have mobility and latency. While the rate splitting enables you to keep having a throughput that keeps increasing because you start allocating power to the private streams here, but as the SNR increases and the multi-user interference increases between streams, you start allocating more power to the common streams. Right. So to conclude, what do we observe here? First important observation is multiple access is very closely related to the problem of managing interference. And multiple access has been heavily dependent on trying to avoid interference when you do OMA, by treating interference as noise when you do SDMA, or fully decode interference when you do NOMA. And what we have with rate splitting and rate splitting multiple access is really the ability to partially decode interference and partially treat interference as noise, and that enables you this flexibility. It's robust because it's information theoretically optimal UF-wise when you have imperfect CSIT. So you know it's a very good strategy. You know you're on the right track because it's grounded by information theory. It's flexible because it copes with any interference level, and it's general and unified because those existing multiple access are sub-strategies of RSMA. And it leads to change to the physical layer and the MAC layer because when I transmit a message, essentially part of that message will now be decoded by other users, right? So that leads to some change and to the system design. And you have many benefits in terms of efficiency, quality of service, robustness, feedback, overhead reductions, robustness to hardware impairment. I did not talk about this, but it's robust to phase noise, user distribution, network load, complexity reduction, lower latency, and so on. You can look at this into and apply this into different scenarios. You can be interested in fundamental limits. You can look at RSMA with different communication techniques. You can have in different systems. You can have in terms of implementation and standardization. There are lots of interesting issues that you can study in this area. Last bit, how is it connected to 5G and 6G? Well, in 5G and 6G, you had a lot of different study, 5G so far, you had a lot of different study items, musts, multi-user MIMO, comp, massive MIMO, network-assisted interference coordination, broadcast, multicast, unicast, all are different study items or work items that are studied separately. And they all form basis to actually create the rate splitting. The rate splitting would actually rely on all those different study items and work items. If you enable rate splitting, you can actually solve all those problems at once. To do that, you need to enable the message split, which is not enabled in the current releases. And it can solve many issues, not only in EMBB, ERLC, and MTC, as I have hinted in these talks, as well as in new services. So if you're interested, as Daniel mentioned, we have this special interest group that started a year ago, where we have this reading, we have tutorials on YouTube, we organize events, workshops, special issues, webinars, and so on. We had our first major special issue in JSAC a few weeks ago, a the deadline is now passed. But if you're interested, I invite you to submit your manuscript to our next special issue in OJCOMS, Open Journal of Communication Society, and the deadline is 1st of December. And with this, thanks a lot for listening, and I will be very happy to answer any questions if you have. Thank you, Daniel.
Thank you, Bruno, thank you very much for your excellent talk. Actually, this is a research area which is again on the course of the day is main fans, and many people started working with splitting. And so now we are going to move for the Q&A section. So feel free to write any questions in the chat box, okay? And so that we can clarify or try to understand more easily in issue related to rate splitting. Okay, so we have some questions from attendees. Let me see. Okay, one question is by Artur Souza de Sena. It refers to the motivation to use to consider generalized rate splitting, because in one of the slides you mentioned, actually you show that one layer rate splitting multiple access already provides some impressive performance gains when compared to normal. Sure. And if you use a multi-layer generalized rate splitting strategy, I think it seems to be much more complex than normal, because you have more layers of successive interference cancellation. So yes. What will be the motivation to consider generalized rate splitting strategy?
So the generalized is obviously, if you can implement this, you get better performance, right? Or you get better performance with RSMA. Let me put the other slide. Sorry, you have this one. Here you have only one SIC when you do one layer RF. Then you can have an architecture. I did not talk about this, but it's actually what we use in FDD massive MIMO. We have two-layer hierarchical rate splitting. So here we have two SIC. And the two SIC enables you to increase the performance even further over one layer SIC. So in RSMA, as you increase the number of SIC, your performance gain always increases. This can be a difference with NOMA. In NOMA, there are some slides where I showed that as you increase the number of SIC, sometimes you have performance decreases. So this is different here. So if you can afford a higher complexity, you can grow and get and go to a 2 SIC, 3 SIC, and so on. But I agree with you that in general, it's increased the complexity. And I think one layer rate splitting is very practical because it has only one SIC, which I think is really implementable. Yeah. Now, why it is useful? It is useful because if you can optimize this, so for instance, this one here, if you can optimize this, and this is something we have done, you can figure out which stream is actually useful under what propagation conditions. So for instance, is it a common stream that has to be decoded by 3 users? Is it a common stream that is decoded by 2 users, as here? Or is it your private streams? And this is why it's very helpful, because then you can tailor, and then you say, oh, I see that those 2 streams are useless, and you can turn it off and design a rate splitting strategy that is really tailored for that application. Yeah. The other obviously usefulness is that if you can solve this, you can show how close your one layer rate splitting would be with this upper bound. And so you know whether there is incentive in increasing the complexity further or not, yes. Right? Yes. Those are all benefits. Yeah. But in all the papers I mentioned and in the literature, I think the most common one is the one layer rate splitting because it has only one SIC.
Yeah, so one layer rate splitting, it arises as a good alternative, right, to generalize it rate splitting.
Yeah, but you see, sometimes it's not good enough. So for instance, in the FDD massive MIMO that we had here, if you do the light blue RS here, this is one layer rate splitting. And the one layer rate splitting does not give enough performance gain because in this case, you have many users And because you have many users, all those users have to decode this common stream, and the rate of the common stream is dominated by the minimum, the weakest users. And so in that case, it doesn't give you so much gain. But if you go to two-layer rate splitting, where you have a common stream for each of those groups, and another common stream for all the users, you can get significant gains. And the gain comes from the fact that you have a common stream at the group level. So that's why I'm saying, depending on the application, you have to be careful. So in this specific application, we saw that having two-layer rate splitting is actually very, very useful.
Okay, thank you, Bruno. So another question by R2 is related to the uplink rate splitting multiple access. Actually,
yes.
It says that it's very clear the advantage of using downlink rate splitting multiple access, but how about uplink? I think you partially replied this question. The question is about the DOF gains and flexibility that we can achieve with uplink rate splitting multiple access. Please comment on this and about the trade-off between performance gains and signaling.
Yeah, so the uplink is a bit different motivation. So in the downlink rate splitting, one layer rate splitting, for instance, does not achieve the capacity. We know the capacity is DPC, right? When we have perfect CSIT. When we have imperfect CSIT, we don't know what is the capacity. In the uplink, we know the capacity. The capacity here is obtained by you transmit multiple streams, and you perform SIC, and you achieve those corner points A and B in the two user, and then any points here in between you achieve using time sharing. This is the classical strategy, the textbook material that you will find in David Say's book, for instance. Some people may call this NOMA, right? So because you use SIC at point A and point B. Now, to achieve this, you need to do time sharing. So actually, if you do this SIC at the receiver, but you do not have this time sharing capability because of latency, for instance, then you actually cannot achieve those points here, and your region will actually drop. You will not be able to achieve points actually somewhere here. You will be limited. With the rate splitting, you don't need to do time sharing. What you do here is you split messages, and then what you see here, you have the first part of your message you decode, then you decode the other users, and then you decode the second part of your message. And so depending on how you split your message and how much power you put to this part versus this part, essentially you can take this point here and you move it along this line, and you don't need to do time sharing. And so when you have constraints, like, or you do, you have network slicing where you have EMBB combined with URLLC and MMTC, and you have constraints, you actually have this benefit of achieving higher spectral efficiency without having to think about doing time sharing. So this is where there is benefit. The drawback there is that, again, you need to split your messages, right? So you need a higher encoding complexity here.
Okay, thank you. Another question is by Sharok Fahment. It refers to the number of antennas that you consider at the base station. So most of the numerical results presented, it's assumed a small number of base station antennas at the base station. So that the same gain can be achieved when you consider, I mean, RSMA over SDMA, if you consider a massive number of antennas at the base station.
So what I showed you is different scenarios. So here, this is the case symmetric, two transmit antennas and two users, two single antenna users. This is a case where you have 200 antennas and you have 10 users. So this is very overloaded, right? You have many more users than the number of antennas. This is also overloaded, more users than the number of antennas. And then you have the massive MIMO, for instance, here, where you have 32 antennas and you have 8 users. So that's underloaded. So you see, those are different scenarios. You can have the number of users is much smaller than the number of antennas, or much larger than the number of antennas. In both cases, you will have gain, but the gain will not be the same. When you're overloaded and you have a lot being overloaded and you have to serve many users, you have naturally more multi-user interference. The gain of rate splitting will be even higher. If you have underloaded with many antennas and few users, and you have very good CSI quality, if you have very good CSI quality, then just using SDMA will likely be sufficient. But as your CSIT quality degrades, or if you have quality of service constraints, or if you have fairness issues, that's where the gain of rate splitting increases. And this is what you see here. You have 32 antennas and 8 users. If you have a CSIT quality that is not great because you have mobility and latency, and that's why you have this big gain that occurs by having our SMA over SDMA. So that's why I was saying you can use in any condition, but the exact gain will really depend on your application and your metrics and your propagation conditions and your CSIT quality and so on.
Yes. Okay, we have another question. I mean, it's a little bit specific. Is in slide 25, the value that you choose for alpha 0.5.
Yes.
So, yeah, was it numerically or is it optimal?
No. So the 0.5, I mean, we just choose 0.5. I didn't go into those details, but essentially what it means is this one. So this is essentially the variance of the error that I have on my CSI quality at the transmitter. And what I'm saying here is that it scales with P, the SNR, and there is an exponent minus alpha. And so if alpha is very large, it says that this variance will decrease very quickly with the SNR. If alpha is 0, it says that actually this is essentially a constant. So the SNR, the variance will remain relatively constant with the SNR. Right. So what the alpha does, it tells you something about the CSIT quality. If alpha is equal to 0, it's equivalent to having a CSIT quality that does not scale with the SNR. And this is what you have typically when you have codebook-based feedback, where you have a certain number of bits of feedback, your CSIT quality will not scale with the SNR. If you have alpha equal to 1, from an information theory perspective or a DOF perspective, it's equivalent to have perfect CSIT. And so alpha equal to 0.5 is something in between, very bad CSIT and very good CSIT, if you like. But you could draw those figures, this and this, for any values of alpha between 0 and 1, essentially.
Okay. Let me see if you have any questions. Okay, I have another question, Bruno, is related to the privacy, security, because in rate splitting, you have the common strings needs to be decoded by all the users. And in that case, how about the security issue? I mean, some users may not want to share their information with the others. So yeah, how can we deal with that?
So this is a question we receive a lot. There is no, I mean, you have to distinguish two cases. The first case is if you have, as in current systems, you have higher layer, encryption, there is no issue here, because when you decode the common message, you actually never decode the final bits because they've been encrypted, right? In the same way, when you do NOMA, the strong user decode the message of the other users. Actually, it never gets to the final bit because it's been encrypted, right? So from that perspective, there is absolutely no issue in terms of security. But you could look at from a physical layer secrecy perspective, and there is different. So there indeed, if you have K users and your eavesdropper is one of the K users, then it will decode the common stream and will already have access to part of the message of other users. So from a physical layer secrecy, that's an issue. And there are a few papers that came out in the past, probably 12 months, where there is an interesting problem there. There is a trade-off between your secrecy rate and your sum rate. So if you want to maximize secrecy and you want to really avoid any users, any eavesdropper to decode this common stream, maybe you need to evolve more towards SDMA kind of strategy. And as you can allow partially a higher rate, higher sum rate, then you can move a little bit more toward rate splitting. So there is a trade-off between secrecy rate and sum rate, and people have been looking at this, and it's quite interesting. So you have to distinguish between those two scenarios.
Okay, I have. Let me see if I have a question. Okay, no question. My last question is about the standardization. So since I mean the goal at the end of the day, the goal is to make it rate split in multiple access and one of the standards, right? Multiple access for the next generation. So how it's going, the process for standardization?
Well, it's difficult for me because I'm not a standard delegate anymore. So I'm not attending 3GPP meetings anymore, but so it really depends on companies. If companies really start seeing the benefit of that, then they will bring it, you know, to 3GPP standard. So that's up to companies, and it's a lot related to the patents they own in this space and all these kind of things. So this is not something I'm very well aware because I don't work for any of those companies. But technically speaking, you can see that essentially all part of the to enable rate splittings are there. Right? If you want to enable one layer rate splitting, it really builds upon multi-user MIMO, massive MIMO. It has a feature of network-assisted interference cancellation, so this SIC or the MUST. It can connect to the non-orthogonal broadcast and multicast as well, as I mentioned. So all those different bits that are done, you know, probably independently in those different study item and work item can really converge towards this rate splitting, and rate splitting would solve issues in there. So currently, I mean, we've been working with some companies and for different applications. So we just hope that, for 6G, companies will push this at some point. But when, I really don't know.
I think you are right. I mean, some current items in 3GPP can be leveraged for rate splitting, right? Coordinated multi-point, multi-user proposition transmission, among others. So
yes, they will probably be seen as, I don't know, they will definitely have, you know, new activities on enhanced physical layer, enhanced multi-user MIMO or massive MIMO, whatever way they call it, or enhanced MUST or something, where this kind of schemes will come in. And then the power of rate splitting is that it can really infiltrate into so many different parts of the systems to boost the performance. And that's what you see from the applications. It goes from classical EMBB to potential application URLC and MMTC, and then also those new services, this ISAC, non-terrestrial systems, integration of terrestrials and non-terrestrials. There are lots of different parts of the systems where actually those techniques could be helpful.
Okay, thank you. Yeah, I think we don't have more questions. Maybe we'll be moving to the end of the seminar.
Yes.
I would like to thank everybody again for attending the seminar. I encourage everyone to take a look in the website, I mean, for the special interest group on rate splitting multiple access. There are many useful information there. Also to submit papers to this special issue in the Open Journal of Communication Society. I think the deadline, I mean, is reasonable, so there is enough time to prepare a paper. So I encourage everybody to submit some papers. And I would like to thank once again Bruno for this excellent talk. Actually, this is as I mentioned, this is a research topic which has gained many fans, and many people are starting working on rate splitting. And I'm confident this presentation will be very, watched by many people. So will be, it has been recorded and it will be available very soon in a TII YouTube channel. Okay, so thank you very much, Bruno. If you have
thank you
your
very
final
much.
words.
Thank you everyone for attending.
Yes, thank you, and see you in 2 weeks in our next Telecom seminar.
Yeah.
Bye.
Bye.
Bye-bye.